Hey everyone and welcome. Today we are pulling back the curtain on our digital world to look at the one thing that really holds it all together: organized information. We're going to talk about the master plan, the blueprint that stops all our data from becoming just total chaos. So let's dive right in.
Think about it for a second. How would you build a skyscraper without a blueprint? Or, say, a car engine without a detailed schematic? You just wouldn't even try, right? Well, that exact same question applies to all the huge digital systems we use every single day. How do you build a university registration system or a massive online store without a rock-solid plan?
Because if you try, the result is pure data chaos. You can imagine it like a library where all the books are just thrown into random piles on the floor. Yeah, you might find the book you're looking for eventually, but it's going to be slow, painful, and super inefficient. In the digital world, that chaos means lost information, broken links, and a system that's just impossible to manage. It's the digital equivalent of that skyscraper collapsing on itself. So, to avoid all that, system designers create a really detailed blueprint first. And this isn't just some rough sketch on a napkin. It's a master plan that maps out every single piece of information, every connection between those pieces, and all the rules that govern them. And here's the most critical part. This happens before anyone writes a single line of code. And in the world of data, that blueprint has a name. It's called the Entity Relationship Model, or, as you'll usually hear it, the ER model for short. It's pretty much the industry standard, the most widely used technique out there for designing the whole structure of a database. It turns fuzzy ideas into a clear, visual plan. And this is not some new thing. The ER model was first thought up way back in the 1970s by a guy named Peter Chen at MIT. Its core ideas were just so powerful and made so much sense that it took off and became the standard for how we design databases, and it's still the foundation for it to this very day. Okay, so how does this blueprint actually work? Well, it's all built on three really simple but incredibly powerful core components. I like to think of them as the nouns, verbs, and adjectives of our data story. First up, we have the entity. This is the noun of our story. An entity is just a distinct object or concept in the real world that we want to store information about. So think of the main characters: a student in a school's database, a product on a website, or a car in a dealership's inventory. These are the core things our system is all about. But nouns on their own are kind of boring, right? We need verbs to connect them. And that's exactly what a relationship does. It shows how our entities are associated with each other. A student enrolls in a course. A doctor treats a patient. An employee is assigned to a project. These relationships are the actions, the connections that make the whole system work. And finally, we need our adjectives. We need to describe our nouns and verbs. These are the attributes. They're the specific details and properties of an entity. So if our entity is student, the attributes are things like student_ID, name, and major. For a product, it might be price and weight. This is the actual data we're trying to capture. Now, here's where the ER model really shines as a true blueprint. Each of these components gets its own special symbol. Entities are rectangles, relationships are diamonds, and attributes are ovals. This creates this simple, universal visual language. It's just like an architect's floor plan. Anyone, from a manager to a developer, can look at the diagram and immediately understand the structure of the entire system. All right, let's zoom in a little bit on that most central piece, the entity. It seems pretty simple on the surface, but there are a few key distinctions that we need to get straight to really understand how this blueprint works. Okay, first off, we have to separate the general idea from a specific example. The entity type is that general idea, the category or the class. So when we draw a rectangle on our diagram and label it student, we're basically creating the template for what a student is in our system and all the details they're supposed to have. Then we have an entity instance. Now this is one single specific example of that entity type. So if student is our template, then Jane Doe with student ID number 151623 is one specific instance of that template. She's a real person represented in our data. And finally, if you take Jane Doe and John Smith and every other single student registered at the university, that entire collection of instances is what we call the entity set. It's the whole group, the actual table of data that our blueprint, the entity type, describes. So let's build on that idea, because it turns out not all entities are created equal. In our data blueprint, some entities can stand up all on their own, while others, well, they depend on another entity just to exist. And this brings us to a really important idea: the difference between strong and weak entities. It all boils down to one word: independence.
A strong entity, like an employee, can exist all by itself in the system. It has its own unique ID, like an employee_ID. But a weak entity, like a dependent, can't. Think about it. In a company's HR system, a dependent, a spouse, or a child only exist in that database because they're linked to an employee. Their very existence is dependent on that link.
And what's really clever is how the database rules enforce this. You can totally have an employee in the system who has zero dependents. That's fine. But you can never have a dependent who isn't tied to an employee. In fact, if you look at the key identifier for a dependent, it's not just its own ID. It's a combination of its parent's employee ID plus its own ID. Its identity is literally borrowed, which guarantees it can never be an orphan in the system.
Okay, now we're getting into a really common but kind of tricky design problem. What happens when you have a complicated relationship between two strong entities? This is where a really cool tool comes in, a special type of entity called an associative entity.
Just think about this scenario. An employee can work on lots of different projects over time, right? And any given project is going to have lots of different employees assigned to it. This is what we call a many-to-many relationship. So here's the puzzle. Where would you store information like the number of hours a specific employee worked on a specific project? It doesn't really belong with just the employee record, and it doesn't belong with just the project record either.
And the solution is actually pretty elegant. You create a brand new entity that sits right in the middle, an associative entity. We could call it something like employee project. This entity's whole job is to manage the connection between employees and projects. And this is the perfect place to store attributes that are about the relationship itself, like hours worked. Problem solved.
So, we've looked at all the components, the different types, some of the tricky cases, but let's zoom back out for a minute. Why do we go through all this trouble to create this detailed blueprint in the first place? Why does it matter so much?
Well, the benefits are huge. For one, the visual diagram acts as a common language. It bridges the gap between the business folks who know what they need and the technical teams who have to build it. Everyone can look at the same blueprint and agree on the plan. And on top of that, a good diagram translates almost one-to-one into the actual database tables, which makes development way faster and less error-prone. Ultimately, taking the time to build this blueprint is the single best way to make sure the final system is stable, efficient, and actually does what it's supposed to do.
You know, a really good way to think about it is like this. The entity relationship model is the bridge that connects the messy, complicated real world with the clean, structured logic of a database. It's the translator that turns our human ideas into a format that a computer can understand and manage.
So the next time you book a flight, order something online, or even just check your grades, take a second to think about that invisible architecture running underneath it all. What are the entities? What are the relationships? And what rules are working behind the scenes? What are the unseen blueprints that are organizing your digital world?